an USRP to add some piece of code. Mainly, it's based on these two USRPs, the B210 with Spartan 6 Xilinx FPGA with a red front-end analog device, an USB interface. But this platform and the gateware is just monolithic. There is no way to modify it to select some processing block to add to the gateware. If you have to modify this, you have to use a text editor and to do it by yourself. The second one, it's a more expensive board with it's X310 with a big Kintex 7. But with A to D and D to A converter, Ethernet, and the interest of this board is the availability of RFNoC frameworks. This is act as a toolbox, so it's possible at the build time to select block with hard-coded sequence, or to select some block additional may be used or not at the flow graph configuration. Motivation of this or to modify the USRP, it's to update the in-stream processing, so to add something, to modify sample, to add some, why not an FFT, or simply to, like this one, to just replace one sample by a tag on a event, on external or internal event, rising edge of a PPS or anything. The second approach is to add some out-of-stream, so independent task, not in the flow, but in parallel. This is demonstration is a two-way, with where for in the case of the CIRT, the X310 use contain the RX chain, but also the parent generator in the same box instead of having two different boxes or different FPGA. First example, again, it's a poster shown yesterday for the demonstration with a flow graph already explained, and for the demonstration, to have something more clear, we have used a pink zinc-based FPGA just because we have this on the shelf. This contains the gateware for the TX part, so the parent generator, and FOMU, a really small board based on the ICE40 FPGA is used to generate both 10 MHz and the PPS. It's just to have something as small as possible to avoid to use, for example, an octoclock or something for the demonstration. Principle is to have a parent generator, 2 mega sample per second. It's configured. This rate is configurable at build time. 70 megahertz carrier frequency. This is fixed, and it's based on the PLL, on the internal PLL from the FPGA. And a GPIO is used as output. This is why there is so filter to remove some frequency to clean up the signal. The second example, more closely, we have the internal scheme, simplified scheme, with a linear shift register, in fact the PRN, with modulation with 70 megahertz and the input. And more closely again, the scheme at the left is in fact the content of the LFSR, the block called LFSR, and in fact there is a PPS edge detector, because the PRN must start, the first bit of the PRN must start on the rising edge of the PPS counter, because we want to generate a specific amount of chip for PRN before resetting the counter and end the PRN to start a new sequence. A prescaler, we have to generate a 2.5 mega sample. So we use a PRN to just generate a tick to update the PRN each time the counter is equal to 0 for a down counter, for example. And finally, we have the PRN. The PRN is updated on when the prescaler tick or when the on rising edge of the PPS. Second example is another project is we have tried to produce using a B210 and a GNU radio and GNSS-SDR a full software GPS receiver and trying to produce the PPS GPS correctly aligned. There is some issue, but it's not another story. So the idea is to integrate the piece of code into the chain to replace or to corrupt a sample by a specific value at the rising edge of the PPS. The idea here is to know the relationship with the PPS and the sample to align this one. It's required to take into account the length, the ref front-end time to convert, and previous block into the chain. The new framer block is not last one in just the chain, so the sample must be also modified, and consequently it's required in first time to know I have this tag. This tag has this specific value into the GNU radio chain, and using something like this, a code like this, to just detect the tag into the stream. The idea here, again, is to use a PPS. This PPS may an internal one. For example, the PPS we want to output as a reference as a PPS GPS or an external signal, totally independent to the chain. When the edge is detected, the output of the edge detect is equal to 1. The MUX select the second input, so our tag. Otherwise, the first input of the MUX, this block here, is used, so the original sample is propagated to the new framer. This is why we have 1, 2, 3, 4, etc. At the output, we have 1, 2, 3, 4, tag, 6, 7, 8, etc. Okay. The question is, okay, we have modified this, but is it relevant to modify the gateware instead of writing a new one? It depends. Modifying is more easy because gateware is already available, everything is ready, the basic chain or the full chain is available, everything to configure the ref front-end or the A2D converter is available, etc. So you have just to add, to inject your piece of code, and it's all. And in fact, writing a new gateware, it's something, it's big task because you have everything from scratch, to write from scratch. You have to deal with the ref front end, you have to deal with everything, and for the specific case of USRP, if you break the gateware, you have to write a new software. So you have the gateware to do, the software to do, and the specific case of B210, the USB 3 is a Cypress, it's a microcontroller with a USB interface in one side and parallel interface in other side. So we have to write a new firmware for this one. maybe it's possible to use the official one, but if you decide to cut everything, to remove everything about Ettus, it makes sense to write everything. So it's big task, and if you're alone to do that, big risk to show the project to become dead with a small after a small time. And in fact, for example presented earlier, just overkill. It's why spend 1 month, 2 months, or maybe 1 year to have something working, plus more or less, just if you have 2 or 3 lines to add. But by modifying the firmware from the USRP, you have to maintain your modification. You have to find a way to store your modification. You have to refresh this modification each time Ettus decide to release a new version, and when the package manager of your operating system decide, I have to update to the next one. So it's a bit boring, and again, sometimes it's maybe a long-term task. And yeah, and maybe one day you have your set of patch, you have the version, and you have to do everything because everything is broken between these two. Okay. So, of course, it's always possible to try to mainline everything or a part of your modification, but it's not always possible. If it's a really specific thing for a specific project, I'm not sure Ettus will be happy to integrate this. I don't know, maybe, why not? Second thing is it relevant to use to modify the gateware instead of using another FPGA? When you work on in stream, when you have to modify sample, it's not possible to have another solution. You have to modify the gateware of your USRP. When it's an independent task, it depends. For CIRT, use the gateware for two-way into your the X310, but the demonstration show it's possible to use another device, another FPGA, and just with default firmware for the B210. But it's a bit more complex when we have to move this bunch of cable. You have a power supply. We need a box instead of just having a small card. And the next problem is the time to generate the bit stream. For the ping, for Z board, the two-way time transfer gateware take around 1 to 3 minutes to synthesize, place, route, generate the bit stream, flash the bit stream. That's all. For a B210, it's 45 minutes around. It depends on the computer. I'm agree. And more than 1 hour if you need to use it with a X310. Again, it depends on the computer. My computer is not the last one. In fact, when you have to, for the test, for the development phase and test phase, if it's possible, for outstream, it makes more sense to use an FPGA independent, just to test your code before integrating it into the USRP. So now we have convinced to the interest of modifying the bit stream, the gateware. So this is more closely how to try to do this with a B210 for when you have to integrate something into the stream. The scheme at the left is more or less the full gateware structure with some level of Verilog files. And the important thing is to find the correct location where to cut the wire and to integrate your specific code. If it's too early, you break the RF front-end calibration. I've tried. There's just, you start GNU radio and UHD said no. Okay. And finally, too late, after this position, the package are modified and many information is provided. So it's more complex to integrate something. Just you have two I and Q sample. It's too complex to modify the stream after this position, this location. A full example, in fact, a patch is available on GitHub on a skimp GNSS-SDR 1 PPS. This demonstrates how to use it. And finally, the idea is in this piece of code, you add a new wire, you add your specific code, and you replace the sample RX. Sample RX is the output of the RX DDC chain, is the input of the new framer. So you remove this by your specific wire signal, and you the RX sample is connected to the input of your code, and the new wire is used as the output of your code and the input of the next block. Finally, it's really easy. For an important task, it's straightforward more because you don't care about how to add your code. The best location is the top Verilog level. It's fine, and in fact, it's just some modification for the makefile. Primarily is makefile because you have for the two-way, since the gateware, our specific code is written using Amaranth language. We had the Python script execution before ISC, because this script produces the Verilog file, and this Verilog file must be known at the launch time, at the ISC launch time, to be integrated into the project. Again, the second makefile, more generic makefile, is updated to add some Verilog file, again, to allow ISC to know this file exists, yes. It's not just a black box, it exists. For outstream with the X310, it's similar, just similar. You have, again, this makefile. This X310_HG is a rule to generate stock firmware, the default firmware for the X310. So again, we have to add our script before Vivado. And this is just to show how to integrate a piece of a new module into the top module. It's just a class. This is a class produced by Amaranth with the enable to start, stop the parent generation. The output carrier, it's another switch. And the PPS in, PPS out, it's copy of the PPS or a new PPS generated as reference, and etc. etc. And you have and we use in fact the front panel GPIO to output or to receive some to receive enable etc. or to output the modulated signal, and it's all. Okay, X310 has RFNoC. So it's maybe stupid to try to use the same approach for the B210 and the X310. RFNoC allows to create our specific blocks, our specific algorithm or piece of Verilog, and to integrate this instead of modifying the gateware. These two schemes are, in fact, the problem, because we need to have a PPS, we need to have a GPIO, but RFNoC blocks are located too deep. This red box is a file generated by a tool provided by RFNoC Image Builder. It's built based on a set of YAML files. So, of course, it's possible to modify the top level, the second level file, but don't try to modify the red box, because this is always overwritten when you use RFNoC Image Builder. So, no way, it's not a solution. In fact, the solution is, again, to modify UHD. And in fact, to modify some YAML file to describe and to add some interface and to explain for example, the PPS may be distributed to the RFNoC block. It's possible. This type of thing, it's always, if you have something, try to contribute, open a pull request. But sometimes, I'm not sure this is acceptable by Ettus. The to-do is for me to create a pull request. And this, my demonstration of my presentation about RFNoC is limited to the FPGA part, because currently the status of how to create out-of-tree block for FNoC is definitively not clear. Google shows some doc workshop for UHD 3.5 with GNU Radio 3.7, or for UHD 4, but with GNU Radio 3.8. Nothing about 3.10. In fact, all workshop, all docs refers to Ettus repository and a tool called RFNoC mod tool. RFNoC mod tool is similar to the GR mod tools, but dedicated to produce base Verilog, libraries for UHD, and libraries and everything for GNU Radio. But I have tried to update this to be compatible with 3.10, but I have stopped when I have discovered Ettus is definitively no more compatible, will be no more updated. The master branch is just empty with a message. Everything about RFNoC for Ettus part is located in a UHD repository. Everything about RFNoC for GNU Radio is located in a GNU Radio repository. And for out of tree block, mainline says coming soon. Okay, but 6 months, maybe 6 months, we haven't same time constraints. So I limit my presentation to modifying the YAML to extend possibilities. In fact, there is 4 or 5 files to replace. 3 are directly into the UHD part. The first one is the IO signature. This file is used to describe all interface used by an UHD. Ethernet interface, AXI interface, clock interface, everything like this. The second YAML file is the board description. In fact, the first one I have updated the first one by adding a PPS EF, PPS interface, with a type slave, because the master slave, as shown earlier, it's the direction of the signal, and with one signal PPS underscore I, limited to 1 bit. The BSP, so the description of the X310 has been updated too, to add into the IO port section a PPS with a type PPSEF, so this refers to the PPSEF for the IO signature, and a drive broadcaster. This means the signal is one to many. The signal, the Verilog code produced by RFNoC image builder has only one input, but this input may be connected to more than one RFNoC block. Again, in OOT block, also you have to specify the need of the signal. This is the left piece acceptor or code with, again, IO port must be updated with a new interface called PPS to be coherent. And with the type PPSEF, it's better to be coherent. And this time, it's the drive is listener. Listener means this is I'm read this signal. I'm slave, finally. I receive. And RFNoC builder use again a specific YAML. This specific YAML describes the gateware, blocks, connection. If the connection is hard-coded, it's not possible, or if the connection is configurable using the crossbar. And again, this file must be updated by using the last line with the SRC block is a device, the device is a platform. The SRC port, the SRC port is the IO port, is a PPS. And the DS block, or block, the name is related to the instantiation done earlier in this file. And the DS port is, again, the PPS. This refers to the IO port in a specific OOT YAML. This time, it's coffee time because it's long. It depends of the content of your YAML, number of blocks used, and complexity. But it's, again, 1 year or something like that. So, OK. In fact, it's good. I have shown how to modify. But why adding code? Some people are free with FPGA development, some others no, and I've talked about Amaranth and some other language, so this is a simple example of some code and how to use it with some demonstration. FPGA, it's not a CPU. In fact, I like this explanation. For a CPU, a code say what it should do. The FPGA, the code say what it should be. It's really different. It's not you describe a sequence of operation, but you describe the behavior of this device. Official, not word, but the classic language to develop for an FPGA. There is VHDL. VHDL is language more European. It's not really verbose, really typed. Everything has a type, and you have to change to cast your signal for some small operation, for some simple operation. It's based on ADA. You have something similar, look like. The Verilog, it's more used, more known for everywhere. It's more permissive, less type. In fact, there is more or less no type. And in fact, sometimes it's a bit of a problem because you have something look like correct, but not working. No error, no warning, nothing, but no, not working. And in fact, you have just forgot to add the signal declaration, but no problem. It's 1 bit. No, I have to 10 bit. No. Bon. System Verilog is an evolution of the previous one with some more feature. I'm not really clear with. I've never tried to. But in fact, these language are synthesized tools, FPGA tools, needs to have as input one of the three language. So everything must be generated, written into this one. But it's possible to use an high-level language to describe your code, and this language produces the Verilog required by the tool. Chisel it's maybe Berkeley language used for some really powerful RISC-V softcore. Spinal HDL is a Chisel fork because author is not happy with direction for the Chisel, so you create your specific new language. And Migen plus Lytix. Migen is a language. Lytix is an ecosystem based on Lytix to provide more core, more real ecosystem with ability to add a CPU, to add some core, to add communication using, for example, PCI Express over to Wishbone, etc. Amaranth is it's not a fork, it's a reboot of Migen. It's again based on Python, and it's a fully new language based on the good thing of Migen and the bad thing of Migen to avoid to do the same error. And it's not an exhaustive list. Flex, C list is definitely a language by itself at the same level as Verilog, VHDL, with grammar, with generator, but at the end it's produced a Verilog, but it's really a new language and not something based on a Python class used to produce Verilog. This new or not really new language allows to have more to be able to have more it's more easy to develop because it's possible to use Python class, Python library. It's possible to use, for example, with the NCO. It's possible to use NumPy to generate the lookup table instead of having to hard code this. So to be more close to this language, to some demonstration, this is it's maybe the assembler for FPGA because it's really low level. It's simple square wave. With Verilog is really small. With a counter, the counter is updated until the value is equal to the max value, or it's resetted if the max value is achieved. And of course, if the reset signal, the input reset signal is used, the counter is set to 0. And you have the output LED is simply equal to the result of a comparator. It may be a Boolean, it may be, no, since there is no information about LED, it's one wire signal, that's all. And the right is exactly the same thing using VHDL language. So first thing you see, it's big compared to the Verilog. And in fact, it's really more explicit. The input and output are type. STD logic is a 1-bit signal. The counter, all signal for Verilog, the declaration of a signal may be done anywhere in a file, but before using it. With VHDL, a specific section of the file where all signal must be declared. It's quite sometimes boring when you have a big file, you have to move before the end to the beginning, to the end, to the beginning when you have to add something. But anyway, and this signal, again, is type to unsigned. It's possible to use another type, ST-logic vector, but this implies to do some conversion just to be able to do the +1. Using unsigned, it's a positive or equal to 0 signal, and it's allowed to +1. Again, for Verilog, the comparator is directly, the result of the comparison is directly used as a value for the output LED. For VHDL, you have to compare value and counter. The result is a bool, and this is used with 1-9 if-else equivalent. If it's true, the value is single quote 1, else the LED is equal to single quote 0. So advantage of this is it's more complex. It's more there are more key to use, but it's more strict. Okay, this is the assembler. Now a bit more modern language. The idea of this demonstration with Amaranth is a parent generator. This is a classical scheme. We have a register, we have a tap. The tap say the location of a bit of the register to use for a XOR. So this one here, we use the LSB, and the next one, the XOR this, using another bit, XOR, etc., etc. At the end, the register is shifted by 1. The least significant bit is removed, and the result of the series of XOR is a new MSB signal. But it's possible to do the same thing with something similar to that, with Amaranth. We have, again, our register. We have our taps. The taps may be live configurable by using an only bit equal to 1 on a tap. Only bit in a reg where the corresponding bit on the taps is equal to 1 is keep, state is keep, and we use XOR, reduction XOR. The reduction XOR is just to say all bits are XORed with the previous one. So this is one, this one, this one, this one, this one, and the result of the first XOR is used for the next XOR, etc. At the end, we have only one bit, and as the previous scheme, the new bit becomes the most significant bit, the less significant bit is removed. And I'm sorry, maybe it's small font, but with Amaranth is based on Python. On Python, you have a class. All Amaranth class inherit from elaboratable class. This one provides a set of methods of set of functionality. We have the init. The init is constructor with some parameters. The output signal is the parent bit. Taps is the taps used to do the end. And the enable is just to update, to allow the parent generation or not. It's a simplified version. So the init, the constructor is only used to store parameters and to declare signal available out of the class during the build time, not the generation time. The second method, elaborate, again, take a platform when it's required to have access to the platform, for example, to have access to the pin, and add a module. Module is a specific Amaranth class. This one provides a clock domain And the first part, the MD comb, it's asynchronous task where we do everything. So the end plus the XOR, this is set into the insert signal. Insert dot equal said it's equivalent to insert equal something. The second one is the output. The output is set unconditionally, so all the time, by using the least significant bit of the register. The next section is a test using M, so the module if to test, enable the signal to allow or not to generate the PRN. If enable is high, we use the MD domain sync synchronous using a clock signal to update the register by using is now equal to the concatenation of the current state of the register shifted by 1. The 1 dot is the same grammar as a Python to select a subset of a list, for example, and concatenate with insert. It's funny because the insert is most significant bit, but here it's opposite order, and the insert is may seem at the first time the least significant bit. And when else is if else classic, the register is set by the default value configured at the constructor time. So the value is left unchanged with the default one until enable is set. Of course, this code may direct generate Verilog. This Verilog may be used, for example, with USRP, or this code may be used directly by another block, another class, and the platform to directly generate the Verilog, generate project file, start, synthesize, place, route, generate the bitstream, load the bitstream into the FPGA. So it's possible to directly to /script name and everything. At the end, the parent is generated without any other interaction. And really, problem with to create a new gateware is if many people are interested by this topic, why not? If you're alone, not sure. And finally, if you spend 1 year to have something starting to work just because you have 10 lines of code to add, it's just stupid. It's better to update your repository, to modify the official bitstream. But in all cases, we are dependent to Ettus. So, thanks.
Just a generic question, I would say. It is, when you are playing with the gateware software like this, of course, as you mentioned, you have sometimes delays that you have to take in account. But you have the delay, of course, from the front end, for example. But after, how you do to calibrate the internal delay of the unit?
One way is simply to inject a known signal into the front end, to have your PPS, and to compare sample between sample corrupted and the known first sample. In fact, I've simply used a switch to just shut down the input.
That was part of the reason for corrupting the stream. So if you do a correlation and you don't know how long the correlation if you do a trivial fear filter, it's easy enough to know how you calculate, but if you do a correlation, it's not completely obvious. And so the fact of introducing this 55AA that you saw was to try to see how long it takes between the trigger of a PPS from the input GPS and the output of this corrupted stream. And so how much delay we have between the corrupted signal and the correlation peak output. And that was actually the reason for introducing this corruption of the data stream, because it will hardly affect your correlation. I mean, if you just change one sample out of a 1023 correlation, it's not going to change the output of a correlation, but it allows you to identify the time delay. Derek, maybe yesterday evening you had a comment about what not to do when changing the X310 gateware, just to make sure that everyone knows about it.
Yeah, this is documented, but this is just a note about the X310 USRPs. There's a PCIe interface in there, and even if you're not using it, don't go in and remove the link to that to the FPGA. That's part of the requirement of the platform. And as the document will warn you, if you remove that and try loading it, then it'll actually brick the USRP. So that is a mandatory part of the FPGA design. But actually, a question about this setup. So you're injecting the PPS into an RFNoC block. I guess a question and comment, something to be aware of is there's going to be non-deterministic latency between the ADC capturing and your RFNoC block, because there's actually a switched bus in there, so you'll get variation there. So the other thing that you have available within an RFNoC block is the timestamps of the individual samples. So you can actually read what the timestamp of the first sample in the buffer that you're processing is.